Welcome back to the part 2 of the video. Here we are going to learn about the classification of the composites. It is based on the matrix materials. There are three major categories: PMC, polymer matrix composites; MMC, metal matrix composites; CMC, ceramics matrix composites. Let's understand each one. Firstly, polymer matrix composites. PMC stands for polymer matrix composites. Here, the matrix is a polymer and the reinforcement is generally a fiber or the particle. Common polymer matrix includes epoxy, polyester, polypropylene, and PEEK. Common reinforcements are carbon fiber reinforced polymers, natural fibers, aramid fibers, and glass fiber too. And PMCs generally provide low density, high strength to weight ratio, corrosion resistance, good fatigue performance, and the design flexibility. In general, the composites will be providing us design flexibility, and the PMC is also providing the same. And they are used in aircraft, automobiles, wind turbine blades, boats, sports equipments, pressure vessels, construction components. The two common examples are CFRP and GFRP. CFRP is a main thing. Carbon fiber reinforced polymer can be taken as a main example for PMC. And the next is MMC, metal matrix composites. Here the matrix is a metal. Common matrix material includes aluminum, magnesium, and titanium. The reinforcement is often a ceramic or high performance material such as silicon carbide, alumina, boron, or carbon. And MMCs can provide high strength, high stiffness, and improved wear resistance, high temperature performance, and better dimensional stability. And they are used in automotive components, aerospace components, engine parts, brake components, and heat sinks. For example, this combination works as aluminum plus silicon carbide can provide improved stiffness and wear resistance compared with the conventional aluminum in suitable applications. And the third category we are going to see is CMC, ceramic matrix composites. Here the matrix is ceramic material and the reinforcement is generally a ceramic fiber. The common matrix includes silicon carbide, alumina, and silicon nitride. The common reinforcement includes silicon carbide fibers and carbon fibers. CMCs are especially useful when you need low density, high stiffness, high temperature resistance, wear resistance, and improved toughness when compared to the conventional ceramics. So these are the things when the requirement comes, CMCs can be used. And they are used in the demanding applications such as gas turbines, jet engines, thermal protection systems, aerospace components, and other high temperature applications. So, why the composites are so popular? Let's look at the major advantages. First is high strength to weight ratio. Composites can provide high strength and stiffness at relatively very low weight. That's why they are very useful in aerospace, automotive, and sports applications. And the tailored properties, that is, this is one of the biggest advantages. Engineers can control the properties by changing the fiber orientation, volume fraction, thickness, and the laminate arrangement. So instead of accepting whatever the properties the material naturally has, we can design the material according to the application is one of the major advantages for composites. And many composites offer excellent resistance to corrosion, moisture, chemicals, and weathering. And this can reduce the maintenance and increases the service life. And the next one is design freedom and the reduced part count. So the composites can be manufactured into complex shapes. Sometimes Several components can even be integrated into single composite component, and this can reduce part, joints, parts, joints, fasteners, and assembly operations. And the next one is good fatigue performance. Many composites perform well under repeated or cyclic loading, and this makes them useful for structures that experiences the repeated stresses. And the next advantage is, so that depending upon the material, the composites can provide the special thermal and electrical properties. That is, the electrical insulation it provides and the thermal insulation it provides. Low thermal expansion or the controlled thermal conductivity can also be attained or can be taken as advantage for the composite materials. And the main thing is lightweight because many composites have low density. They can reduce the weight of the transportation systems. And lower weight means lower fuel consumption and better efficiency for a longer range. So, not that everything has advantage and not everything is perfect. So, this also has some limitations. So, first one is brittleness. Some composites can be more brittle than metals. They can experience matrix cracking, delamination, and fiber breakage, followed by repair challenges, that is difficulty in the repair. Repairing the composite structures can be more complicated than repairing the metals. So it may require proper surface preparation, controlled curing, special equipment, skilled technicians and inspection is required. Next one is environmental sensitivity. Some composites can be affected by moisture, UV radiation, high temperatures, chemicals, and solvents. So the proper material selection is very important. And the next is cost and manufacturing complexity. Advanced composites can be expensive because of the costly fibers and the resins and the specialized equipment and the need of the skilled labor and and controlled and strict process control. Due to this, the manufacturing cost will be very higher. And the processes such as autoclave curing, resin transfer molding, and filament winding can also increase the manufacturing complexity. And this also leads to the high manufacturing cost and complexity. And the last one is limited recycling. This is a major challenge, especially for the thermoset composites, because the polymer matrix is cross-linked and it cannot be simply be melted and reshaped like a thermoplastic. So the recycling and end life disposal can be very difficult. And another such a behavior is anisotropic behavior. This is a very important term to remember. Anisotropic means the properties that depends on the direction. For example, an unidirectional carbon fiber composites can have a very high strength along the fiber direction, but much lower properties perpendicular to the fibers. Therefore, the fiber orientation is extremely important in a composite design. So these are the disadvantages of the composite materials. So let's have a quick revision. So the composite is basically matrix plus reinforcement. The matrix holds and protects the reinforcement and the interface helps transfer the load between them. So there are three major categories: PMC, MMC, and CMC. Their major advantages are high strength to weight ratio, corrosion resistance, tailored properties, and design flexibility. Major disadvantages is anisotropy, recycling challenges, difficulty in repair, manufacturing complexity, and higher cost in the manufacturing process. So the next time you hear the word composite, don't just think of the carbon fiber, think of the very basic principles, different materials plus different composites which works together to give a material designed for a specific purpose. So that's the beauty of the composite materials. If you found this explanation very useful, subscribe to the RPG Simplified and share it with your friends who are studying related to these fields. I'll see you in the next video. Keep learning and keep simplifying. Thank you. See you in the next video.